Hello, CNBT 1311 again. This is part 2 of the chapter 1 video walkthrough. We left off with precipitation. If you'll remember in chapter 1.1, we talked about lighting. We left off with the direct lighting coming into a house, bouncing it off the walls and stuff like that. All right, let's go over here to precipitation. Precipitation is rain, and we get a lot of that down here on the Gulf Coast, as you well know. So what you do with it is very, very important. A poorly designed structure, a poorly designed site that does not take in consideration rain runoff, you're just asking to be sued. I did the forensic engineering on a building that collapsed due to water ponding. The roof drains up here were clogged up. The maintenance people did not go up there and make sure that they were free flowing. And sure enough, we got one of those 1.5 hour per hour rains for about 6 hours, and it basically turned the roof into a swimming pool, and it could take no more, and the structural system bowed and bent to the point that it pulled the joist off the columns and the roof collapsed, and it was a big mess. But I got to go tell them what happened as an engineer. So we reverse engineered the failure. We call it forensic engineering, and did a lot of forensic engineering in my past. All right, let's get back to the book. Now, the amount of annual and seasonal precipitation expected for a building site should influence the design and construction of the roof structure of a building. Well, no duh. You think? It ought to influence the design of your parking lot, the size of your storm sewers. Most of our streets in Harris County are only designed for about 1.5 inches per hour rain. You get anything more than that, you're going to start having ponding water. You get past 2.5 inches, you're going to have some flooding. And after that, well, people just go crazy. So yes, it influences everything, because your roof scuppers, these drains up here and the down pipes, and all of this has to be designed to carry the amount of water that is being collected up here. And you see this particular structure is a flat roof, okay? Well, it's probably got like 1/8 of an inch per foot. But when we get to roofs, we'll talk about all that stuff. And if you really want to get deep down in the weeds, and you probably don't, we can go through and design how big your gutters need to be for a particular roof slope. But anyway, so we've got some water that's coming off of here. If it's really sloped, I mean something sloped, because here's a parapet with a scupper, and there's a downspout. Flat roofs require either internal roof drains or scuppers, and you better have both. If you got a flat roof and you're draining it to an internal, you better get your structural engineer and figure out what's the maximum that roof can hold, and you better have some overflow scuppers over here, so that in case you do have blocked roof drains, before it gets to the point that it's overloading your structure, your roof structure, then you'll have an emergency overflow that comes out. A lot of buildings will have these where they come out and they've got a spout, a spigot. So anytime you see water when it's raining coming out a wall through spigot, then you know your roof drains up here are clogged up. All right. So now this is in the older buildings downtown Houston, they used to have a lot of these roof cisterns for collecting rainwater, and they would serve like what Ching says here is a primary backup. They would treat them. They would treat the water. They can also use it to the water the landscaping around the structure. A lot of the old buildings in downtown Houston used to have roof cisterns. A lot of houses out in the rural parts of the world, they have underground cisterns or above ground cisterns. I have a friend that's got some property out in the hill country. They don't get much rainwater, and he's got a tank, and the water comes off his roof, and it goes in and it collects in this giant 2,000-gallon tank. So when he goes up there on the weekend, then he's got rainwater, and they treat it. It goes to a small little in-house treatment system, and if he needs to, he can buy water and have it trucked in and fill it up. Water is a very critical thing. I did a lot of water and wastewater treatment plants. In fact, I did three of the world's largest wastewater treatment plants as an engineer. And as we continue to evolve or de-evolve in the world today, water is going to be fought over like oil and gold. All right, well, enough of my soapboxing. Now, obviously the pitch of the roof, and you know what a pitch is. A pitch is the same thing as a slope, okay? How much drop or rise over how much run. We'll use this as an x-axis because I'm also a machinist and an engineer. And Rene Descartes said the vertical was the y and x is the horizontal, just because. That's what he did. Cogito ergo sum. That was one of Descartes' sayings. I think, therefore I'm alive. So Rene Descartes is the father of modern mathematics and philosophy, and came up with the Cartesian coordinate system, the x, y, z system that all long-range shooters use, and z, not another y, you goober. There we go, z, all right, and machinists use, and engineers, and even architects. All right, well, let's get rid of this. I digress. I get off into geek land. All right. You on the front row, I'm expecting you to hold me back when we get to structural stuff, because I'll probably get all, ooh. That's right. We don't have students face-to-face here, do we? This is a lecture for an online class. Oh, well. Well, send me an email or something and tell me to slow down or get off of Geekville. Okay, well, anyway. So depending on the pitch of the roof will depend on what? How easily the roof sheds water or snow or ice, which brings us to another issue. If it's super pitched, guess what? It's going to shed rainwater quickly, but the velocity of that water coming off that roof is going to be faster than the velocity of the water coming off of a less steep roof, right? Now this is going to hold more snow. This theoretically will hold less snow, but if you go up to like a place like Crested Butte, which they get like 12 feet of snow a year, they got some pretty steep roofs, and these roofs also have like little stop things going up there so that the snow catches and the ice will catch on there. Then they pay people to get up there and shovel that off. If not, you got this big chunk of ice that's going to slide off the house and squish you. Okay, you'll be going out your car. Oh, let's go play in the snow. And then all of a sudden this stuff lets go and you're buried. Oh no, Annie M. Last time I was at Crested Butte visiting my son, there was a lady who was killed by a sheet of ice that broke loose from her house, believe it or not. All right, well, we'll resurrect this person after we've done them dirty. Okay. Well, okay. All right. So that's the point here, is that you got to look at the slope of your roof and how steep. So if you're in snow area, you'll have a building code and rules of thumb to follow there. Okay. All right. And like down here, the size of these gutters, is it going to be a 3-inch gutter, 4-inch gutter, a 6-inch gutter? Okay. If the angle of the slope is greater than 60 degrees, the roof may also be able to slough off snow. Well, sloughing it off and holding it and then building up an ice sheet, if it's not insulated real well, can also give you problems. All right? All right. But all your downspouts and then your underground sewer system, if you're going to dump the rainwater in the sewer, has to be sized for the amount of runoff you're getting. Right, and that varies from area to area. Site drainage. This will get you sued if you're not careful. Where are we at over here? I'm going to watch my babbling. Oh, we're at 11 minutes. Okay. Okay. I want to hold these to about 45 minutes. Development of a site can disrupt the existing drainage pattern and create additional water flow. We already talked about this earlier, didn't we not, in Chapter 1, about getting with Harris County Flood Control and getting a permit if you're going to develop a new site. You may have to dig a retention pond to hold some of that rain off because the bayous and creeks can't take it. If you change the water flow on your property and it adversely affects your neighbor's property, you can get sued. It's against the law to do that, in Texas anyway. Same with what you're building, and that's what Harris County Flood Control will look at. How much concrete are you putting down on a non-paved area? Are you putting down a parking lot? If you're going to develop the whole thing in a non-pervious covering, let's say you're putting in a little commercial building. So you've got the building, you've got the pavement around it. This is going to equate to X amount of runoff. They may say part of your parking lot is going to be a retention pond. And you'll have to figure out how to park less cars. You don't want to limit or disrupt the existing hydrology if at all possible. Now, in the scenario I gave y'all in the Chapter 1 video where your backyard turned into a swimming pool because it was all just messed up, well, you got to figure out how you're going to control the flow coming off of that. All right. So finished grade should be sloped to drain surface water away from the building. This says 5% minimum. Again, your mileage is going to vary here. Okay. We don't see too many foundation drains down in this part of the area, this part of the world. There are some on the big buildings. You have subsurface and surface. This is important for you to make sure. You have subsurface and surface drainage system. Subsurface drainage, that's stuff that's underground. It's the B inlets in the middle of a parking lot that goes into a storm sewer. But that thing then dumps out into a ditch or a bayou. Okay? Let's see. You get too much groundwater, and yes, it can reduce the load carrying capacity of a foundation and soil. So again, that goes back to your soils engineer. All right. Surface drainage refers to the grading. That's obvious. Okay. Area drains, and down here in Houston, you will have a set of specs from City of Houston, Harris County, of the type of drains you're allowed to put in these public areas and roadways, whether it's a B-type inlet, a BB inlet, an E-type inlet, and that sort of thing. And the size of the RCP, reinforced concrete pipe. Here's a head wall. That's called a head wall. There's no charge for that. That's a head wall. And the water would go through there and dump out into the creek or the water retention area. Wind. We talked wind. We talked about passive architecture stuff. Claudel Rollins Scott, they had an elementary school that was basically a long shoebox, and they would have a high window over here on the leeward side. The leeward side of the building, College Station, back then, before it was developed as much as it was, that's the leeward side, okay? And this is the windward side, where the wind predominantly comes from, okay? Wind side, all right? Wind side. So the air would flow through here and then rise up across and go out a smaller opening on the lee side of the school. And it increased the velocity of the air, and it helped keep air flowing in here. And they did some high-tech insulation back then, as high-tech as they could. The foam technology hadn't been developed as well as it is today. We have some excellent insulating foams that are not formaldehyde based. They don't produce cancer, and when they burn, if they burn, get hot enough, they basically throw off water vapor. So anyhow, as long as it's installed properly. And we'll talk more about foams in the thermal chapter. Roof overhangs, you can read about all this, how the different overhangs affect. Now these things cost. These things cost money in your design. You may not be allowed to do this. Roof overhangs increase incoming airflow. But why? Because it traps the air and kind of funnels it through there. So I mean, I guess in a perfect world, you could have this giant funnel out here. That'd be like really funky, and all the architects would laugh at you and say, "Oh, what kind of moron are you?" Right? But that's basically what you're doing. Wind's hitting the ground. It's hitting your overhang. It's forced through this opening. And this is not an engineering course, but you know that for a given velocity of air, if you're forcing it through a smaller opening, then temperature drops and the velocity increases at that point. Bernoulli's equation. But I digress. All right. And there are other ways you can handle it instead of having this, like this was a concrete roof. You would have to form that out. You could put, when we talked about shutters and overhangs and stuff like that. So this could be an external thing, as long as it's designed for the wind load, so the wind doesn't rip it off. Partitions can do certain things, can change assuming you have a constant airflow pattern. And louvers can beneficially direct and diffuse airflow. Now, growing up in this area along the Gulf Coast, it used to be extremely popular to have what was called an attic fan. Attic fan, here's the ceiling, okay? It was this fan, huge fan. And then it would have louvers, and the louvers would open when the fan would turn on, and you had this giant fan, okay? And you'd crack the windows in your house, and this would be the roof. This is the roof of the house. And at the end of the roof would be a gable vent. This is a gable vent, okay? This is a gable. This is a vent, okay? And so the walls of the house would be down here with the window. And you flip the switch, and man, you could suck air through these windows, up through the attic, and out through the ceiling, and it would reduce the heat of your attic, and it exchanged the air in the house. And let's say the house was locked up for 2 or 3 days, and it was hot, and we didn't have central air back then. We had window units, but not in every window. And you could immediately get the internal air of your house to the ambient air outside, okay? And then you could turn your air conditioner on. And it would also exchange the air in the house. And then if mom was burning something in the kitchen, you could use the attic fan and it would suck the smoke out of the house pretty quick. So when you're thinking about all this, this is like wind electricity, right? Those wind farms. If the wind's blowing, you got electricity. If it's not, you don't got electricity. If the wind's blowing, yeah, this all works great. But if the wind doesn't blow, what are you going to do? Okay. Well, then you got to have an alternative. You got to have a plan B. Some way to mechanically get the air to move. Okay. So, how did Claudel, Rollet, and Scott do that? On every one of these openings, on each side, they had a fan. It was sort of like an attic fan, but it was turned vertical. So if they needed it, they could use it to suck air through. All right. Let's see. Okay. Remember windward. Remember leeward. Wind shadow. I love it. You're out sailing and you say wind shadow, you're going to get thrown off the sailboat. It's the windward side or the leeward side. So what they're talking about here is what's down here in the suction part of, here's a pressure eddy. In other words, right before all this air comes up over this, you're going to have some of this air that comes down here and spins around. And the same on the inside. It's going to want to go to the path of least resistance. Okay? So this would be like, they're giving an example of high wind breaks. And he talks about this up here. All right? It could be an earth berm, could be trees, could be anything to block the wind. All right? So that's assuming you can orient your site to your wind. We talked about that in our site development, did we not? All right, structure components. Here's a pet peeve of mine. Most people don't understand how air works. Okay. So let's say the wind's like coming across here, right? Okay. You got high pressure on this side of the wall. In other words, the wind's pushing it. You got low pressure over here. That's how a Marconi cell works on a sailboat, right? You got, or an airplane wing. The air flows over the foil shape and you produce low pressure and high pressure, and it sucks you into what? The low pressure. All right, so in this case, you have wind coming across here, and let's say there's a tornado. Woo, yeah. Okay, got super high wind, or it could be a hurricane. Okay, and here's the Wicked Witch of the West on her bicycle. Okay. Okay. And poor Toto is back here trying to escape. And anyway, so you got high pressure on this side of the flat wall. You got low pressure. In other words, this is trying to suck the wall out. This is trying to push the wall in. And guess what happens on the roof? It's trying to lift the roof up. Trying to suck the roof up. Okay. Now, on slopes of 7 to 12, same thing happens. You still got high pressure. There's your high pressure side, your windward side. And here's the leeward side. The low pressure is trying to suck it out. And she's still riding her bicycle. Okay. All right. And the roof's trying to get sucked off. And this would be in the shape of, let's assume this is a mechanical metal building. It's a rigid frame. So this thing is going to be like pushing over this way. This will be pushing up like that. This will be pushing down a little bit, but it's trying to suck the panels off the roof and suck this side of the wall out. Now, what about super steep roofs? Now, it makes sense, right? That if this is high pressure and the flatter the roof gets, the more vertical this gets, based on its run, you're going to have high pressure up here too, right? It's going to be trying to push it in, and then on this side, you're going to have low pressure because the wind's going to come across here. It's going to be mounding up. It's going to hit this. It's going to come up over, and then it's just like an airplane wing. It's going to be pushing, and then over here it's going to be sucking, and same way on the wall here. Because actually the wind, depending on how the velocity, it'll start to collapse. And underneath here will be a very low pressure eddy. It'll be sucking it this way. Okay? All right. Now, again, I'm not expecting y'all to be engineers. I'm not expecting y'all to be as all excited and geeky as I am over this kind of stuff. But trust me, you screw your wind loading up on a structure, there's another place for a lawsuit. Okay? Again, remember the three little pigs. The last heavy brick house, the wolf couldn't huff and puff and blow their house in. All right. So everything on that building, and this Ching talks about it in here. He talks about the cladding and all this other stuff. What does he say about wind experts? Negative pressure or suction on the sides of leeward surface in normal. Okay. These are also in your building codes. Okay, depending on what part of the universe you're from. Now, if you're up in Tornado Alley, up in Kansas, and stuff like that, oh my God, yeah. You can do whatever you want. About the best thing you can do for tornado-resistant structure is a monolithic dome. You can go Google Texas domes, monolithic domes. They're up in Little Italy, Texas, which is up off I-35. Before you get to Fort Worth, Dallas area, between Waco and that area. And they're foam structured and concrete domes. They'll survive a tornado when nothing else will. And you know, it makes sense, right? All right. All right, now how about sound? How are we doing on time? How are we doing on time? Oh my God, we're 27 minutes. We're just looking at megabytes. 27 minutes. Okay, we're fine. All right, sound and views. Okay, depending on the windows that in the house, the type of material the house is built out of, everything has a resonance frequency of its own, a hysteresis value. How easy does it transmit vibration? And that's what sound is vibration. Now read through this. Y'all read through all of this. I'm not going to bore you and read this to you. If you can orient your building so that the opening walls are facing the most noisy part of the road or highway near the structure, well, yeah, then you'll let that solid wall help abate some of that sound and noise. You use double pane insulated windows that are foam filled, the frames, the right kind of insulation and the right kind of building material. Masonry and good foam for your insulation will certainly abate the noise. The doors, what are the doors made out of? Are they solid core foamed structural doors, or are they just El Cheapo hollow fiberglass exterior doors? If that's the case, then they're going to transmit more noise. And all these LED credits are part of that LED thing. And don't forget the LED, what it stands for. You're going to have the book anyway when you take the test. And if I ask a question, what's LED? Well, you can either Google it or go to that section of the textbook, right? Again, we're not here to beat you up. We're here to get you through this vocabulary so that you can move on with your architectural design path. A window may be created within a wall in a number of ways. Well, no kidding. I've put windows in walls that were solid. I took a chainsaw and cut the frickin' opening and then reframed it for the contractor I was working for, because the architect wanted a window and he forgot to put it on plans. That was fun. And so windows, how you frame them, what they're made out of, all of this affects, um, um, here's some good rules of thumb, okay? South-facing windows can effectively shade. Uh, your north-facing windows are exposed to winter winds and cool climates, but the artist, painters and sketchers and artists and natural light photographers, they like the north lighting because it's the softest light, as they say. East and west facing windows are sources of overheating and are difficult to shade effectively. Well, that makes sense, doesn't it? Because where does the sun come up? It comes up in the east and it sets in the west. So if you've got a shoebox shaped structure and you can orient it so that the smaller sides are facing east and west, then you've reduced the heat load on two sides of your building. Regulatory factors. We already talked about topography, right, and flood control. Well, guess what? There is a plethora of ordinances and building codes and zoning codes that you have to adhere to. And depending on where you are in the United States, or even in Texas, you may have a zoning ordinance that will or will not let you do certain things. Your deeds and covenants, your homeowner's restrictions, let's say 51% of the first floor has to be, or 51% of the structure has to be masonry, or something like that. Some of them say the outer facing, the back of the house can be siding, but the front two sides have to be brick. Some say that the whole first floor has to be wrapped in masonry. This talks about your mileage is going to vary. Do not use this as a hard and fast thing. All right, you need to check your local code, your building code, your property code, and if you're building a building inside something, like say the Vintage over off of Louetta and 249, if you're going to put a pad site in over there, I guarantee you that developer is going to have certain restrictions on what they want it to look like and not look like. Then you have to have the Harris County Engineering Code, your fire code, your plumbing code, and whatever other codes that are going to be impacting your deal. Sometimes you'll have a height restriction, okay? A square footage restriction. So let's just say this is your building, your site, your property lines. Well, you can't put everything on that property. You got setbacks. These are required setbacks. And not only are you have required setbacks, you'll also have easements in here. This may be an overhead HL&P easement that you can't build anything underneath that. You may have intex. Intex. I just dated myself for natural gas. Okay. Then AT&T has their buried cables back in here. That's underground. And then Billy Bob's pipeline or something. Okay. So all of this should be on your plot. This should be on your deed, your meets and bounds, which your surveyor should give you, your licensed surveyor. And so let's just say that the deed restrictions say you have to have a minimum of 300 square feet. 3,000 square feet. 300 square feet, that'd be like a fifth wheel. 3,000 square feet. Well, based on the setback and where my garage needs to be or my parking needs to be, I can't put 3,000 square feet in a single story. So I got to go up. I got to have a two-story structure. And then some deed restrictions will say two-story structures must have a minimum of X amount of square feet on the bottom floor and a minimum of so many square feet on the top floor. and it may not be the same. So you might be able to get by with a story and a half or a full 2-story. Again, now you're forced to build a cube. But I wanted to make some architectural statement. Well, then make an architectural statement with your cube because you're stuck like Chuck. Okay? Again, what did I say in the first video? It depends on how big your site is and what you're going to do with it. I mean, they're not going to let you put in a petrochemical refinery plant inside a subdivision. You're going to have to go to a place that can support that. Right? All right, zoning ordinances. We already talked about that. All right. Possible projections of your zoning ordinance. All right. This talks all about your exclusions to the general requirements of the zoning ordinance. All right. If you're up in super snow country, I bet you my bottom dollar they're going to have an ordinance or a design. The insurance companies will have a code they're going to want you to design that structure for the snow loading and the other stuff. We talked about allowances for heights. This talks about it here. And you thought I was making that up. All right, setback 2, setback 1 can be this height. Setback 2 can be that height. And there may be another setback that can be that height, a different height. Again, these are your restrictive covenants and your zoning ordinances, and some of them even refer you back to all those LED things. Your mileage is going to vary. Again, this is a survey course. This is to get you into what is out there, lurking in the darkness. Site access and circulation. This is where people get into a lot of trouble. All right, what do we mean by that? Providing for access and circulation for pedestrians, automobiles, and service vehicles is an important aspect of site planning. Now, your emergency vehicles are also service vehicles. You've seen a lot of these red painted stripes around these parking lots. It's fire zone, towaway, you can't park here, and that sort of thing. And it's because they got to be able to get in there to do their business, okay? Can't send a suppression crew in here if you have to make a park over here and drag all that stuff over there. So these are 12 points for possible aspects of what you have to allow for in your access and circulation. Big thing is, what's the population density? Let's say this is a commercial building. How many people are you going to have here, plus your employees? Where are they going to park their cars? Do you have enough room for a parking lot? The Vintage Shopping Center is a quaint little place of all kinds of stuff over off of Louetta and 249. And it is a prime example of some of the poorest design parking on the planet. Sometimes it's hard to find a parking spot over there. You're not going to find it near those drive-up facilities most of the time. You've got to park out in the big parking lot out in the South 40 and then walk, which is not bad. But my whole point is that, yes, it's quaint, and yes, there's parking in front of these shops, but it's very limited in front of the shop. So you have to go out in the main parking lot and then walk. Now, is that a bad thing? No. It's a thing. That's how they designed it. They were limited to X number of parking spots along the thoroughfare of how they're going to get the traffic to move through the Vintage. Okay? All right. So these 12 points you need to read and just kind of put back in your Rolodex. I'm not saying memorize it. You know where it is in the book. The book has an index and that sort of thing. All right. Let's say this was a medical facility. Okay. Most of your employees would probably try to park your back in here or something. Okay. But then again, what about service people? And that talks about that all in here. We beat that up enough. Here is a good part of human factors. Pedestrian circulation. Okay. 3 foot minimum for one person. 4 foot for two. That's a little too crowded for me, but I'm kind of a socially unacceptable person anyway. Side by side is really 6 to 8 feet. Okay. And then if you're going to have somebody walk and you got these cars hanging over, another 6 feet. Again, this is a rule of thumb. Now, exterior stairs. Stairs will get you sued if you screw these up. And we'll have a whole section on stairs. You'll probably hate me by the time we get done with stairs. But minimum of 3 risers per run. Handrails are required for stairs having 4 more risers, or where icy conditions exist. But anyway, okay. And bike paths. Again, these are rules of thumb. You may have a zoning requirement or a building code requirement in a certain area that requires something more. Okay? Seriously, when we get to stairs, y'all pay attention. We'll have some stair calculations if we can fit it in. If it was a face-to-face 16-week class, you'd be doing stair calculations a lot. Because, I mean, that's vertical movement of a human and how you get them to move and how you get them up. Those of you who are taking face-to-face classes out at the Cypress Center, go look at all the different stairs we've got. That big Mayan sacrificial staircase right there by the cop desk, and then go look at the other 2 stairs on the end. And avoid surface irregularities that can impede wheelchair traffic. Well, no, that's a part of the ADA thing. And there's a whole section on ADA later on, okay? So ADA is the American Disabilities Act, okay? There's a whole section of human factors on designing around ADA. When I remodeled my bathroom at the house, I made sure that I could get a walker and a wheelchair back into the bathroom. Not that but with my 2 knee replacements and my back surgery, I was using a walker for a while. We were glad that we did that. Curb ramps. If you're going to have an ADA access to a doorway in a building, you need some kind of wheelchair curb ramp. Yeah, and you need to have the buttons where they can get to it, not out in the flower bed like at the Cypress Center main opening. Yeah, they had ADA ramps going in, but the ADA button on the exterior was 3 feet out in the flower bed. And since I opened that center as the director, that was one of my first pet peeves. And they had to go pour a slab out underneath the roof covering to get to the button. So the poor person in the wheelchair, if it's raining and they finally make it up into here, they got to go back in the rain to push the button, and so the door's to open. Go figure. Okay, not a very good design. All right, these are some rules of thumb for ramps. I mean, you don't want them so steep that the people are out of control, right? And a ramp is nothing more than what? It's a rise over a run. We go back to the right triangle again. Okay? All right. Vehicular circulation. This is civil engineering. This is civil engineering. I am not going to expect you to be a civil engineer. But trust me, parking lots, I have gotten into a lot of arguments with architects over parking lots and how to move cars in around their structure. And sometimes they had to narrow their building to get the number of cars that they needed in the spaces. Okay? These are some rules of thumb. Again, these are rules of thumb. This loading berth, 10 to 12 feet wide and 35 feet to 50 foot long, in this radius, in my opinion, is too tight to expect a truck driver to get that in there. Okay? Especially in this little slit here. A good truck driver can do it, but he's going to have to come in this way, get that thing jacked over to back in that way. So he may have to actually go against traffic. Okay? Because having him come in this way and then make that steep turnaround. He's going to need this. So anyway, these are all things you got to consider. And I've had a lot of arguments with architects in my other life about this. Parking lots. We already talked about the vintage parking lot. Now, if it's just out in the middle of the pasture, like the big parking lots at the vintage, that's a no-brainer, okay? You know, they're pretty much like this. They're double stacked. They're 90 degrees in. These get a little hinky. Angled parking lots, okay? Some sections of the high-rise parking garage at UP campus have some angled parking slots, and you got to watch your cross flow traffic. You can get your cars backed in or headed in deep enough, and then get them out. But these are some rules of thumb. Again, this is a ramp. You don't want the ramp too steep; the cars bottom out. And what is this? Well, that's a right triangle, isn't it? Yep, that's a right triangle. Look at that. That's a right triangle. Again, right triangle. And this is a right triangle. That's all slope is. Rise over the run. Okay? You got to get these angles right. Okay? Ching says transition slope equal to 1/2 of the ramp slope. Okay, well, that's fine. That may work. It'll work for some cars. Now, low riders, they need a more shallow ramp, right? But a standard vehicle, this is for standard vehicles. All right. ADA parking in garages for wheelchairs, accessibility, ADA accessibility guidelines. All right. Okay, where are we at? And we're at 46 minutes. Oh my goodness. Probably because I yapped too long. We're at slope protection. I tell you what, we're going to do 3 videos for chapter 1. All right, we'll start off with slope protection on the 3rd. We'll start off with slope protection.